Welcome to this explainer. Today, we're diving into a highly actionable step-by-step tutorial on mastering test-driven development, or TDD. Look, if you write code, manage developers, or honestly just care about shipping software that actually works, we're going to explore exactly how to do that together. Let's kick things off with a classic developer nightmare. You know the one. Think of our case study subject, Jimbo. So Jimbo builds this absolutely perfect discount function that applies a 10% price cut. He tests it manually once, it works beautifully, and boom, he calls it a day. But a few days later, the product manager completely changes the rules. They say, hey, let's apply a 15% discount, but only for prices above 500. Jimbo hacks the new logic in, right? But because he doesn't have a safety net of automated tests, he unknowingly breaks the logic for the lower-priced items. The whole system literally fractures. So, to make sure that never happens to you, here is our roadmap for today. We're going to define the problem space, walk through step 1, which is the red phase, step 2, the green phase, and step 3, refactoring. Then we'll cover isolating your tests and wrap up with TDD in the real world.
All right, section 1, defining the problem space, requirements first.
Okay, your very first actionable step here is translating massive, kind of vague project themes down into actionable user stories for your developers. You start with a big theme, break that down into epics, and finally distill it into user stories and specific tasks. A user story frames the requirement perfectly. For example, as a developer, I want to extract and combine all digits from a string into a single number so that I can process mixed input strings. See how that works? It gives you the who, the what, and the why right up front.
Now, once you've got that story, you actually need a way to prove it works. We define what done means by writing acceptance tests, and we do this using Gherkin syntax. Gherkin is just a fantastic tool because it relies on plain language. Literally anyone on the team, from the hardcore backend engineer to the non-technical product manager, can read it. It's a real game changer for improving communication and trust across the board.
For example, we structure our story by using specific keywords. We state, given the input string as ABC123AB! When I run the number extraction function, then the extracted integer result should be exactly 123. It's incredibly clear, right? There's absolutely zero ambiguity about what this function is supposed to do. Moving right along to section 2, step 1, the red phase. This is where we write a failing test. Test-driven development is this ongoing rhythmic cycle of 3 actionable steps: red, green, and refactor. You are basically going to live and breathe in this loop, and it all begins with the color red. So in the red phase, our primary directive is to proactively automate our unit tests, knowing full well that they are going to fail initially. I know this feels kind of counterintuitive to a lot of new developers. Why write a test for code that doesn't even exist yet? Well, because the test becomes the blueprint.
You literally write the Python test first. Notice how we're asserting that if we pass the string A1-B2-C34 into an extract numbers function, the result equals 1, 2, 3, 4. When you run this test, your console is going to light up with red errors. Why? Because that target function hasn't been written yet. That puts us firmly in the red phase, and believe it or not, that is exactly where we want to be.
Next up is section 3, step 2, the green phase. Let's make it pass.
Okay, in the green phase, you've got to put your ego aside. You aren't writing a masterpiece here. You are writing just enough code to satisfy the automated checklist and turn that test green. Seriously, don't worry about elegant design or perfect efficiency yet. Your singular goal is just to make the error go away by satisfying the test condition.
So here is the actionable step. Just write the basic functional logic. In our example, you write a simple function that iterates through the string, checks if a character is a digit, joins them together, and returns an integer. When you run your test suite now, the tests pass successfully. You have a green light. The code works. Boom, on to the next step.
Which brings us to section 4, step 3, refactoring code. It's time to clean it up.
We use the refactor phase to improve the internal structure of the code, but, and this is absolutely crucial, without ever changing its external green-lit behavior. Because you have a passing test protecting you, you can confidently rewrite the messy code you just threw together in the green phase. If you break something, the test instantly turns red, letting you know you went a little too far.
During this phase, you want to actively hunt down a checklist of what we call bad smells. Are your methods too long? Is there duplicate code? Does a single method do way too many different things, which is known as bad cohesion? Or maybe it relies on too many outside systems, which is bad coupling.
You want to sniff out these issues and squash them right now.
Next, actually clean up those bad smells. You can structure the code beautifully by adding clear, comprehensive documentation at the top so future developers know exactly what it does. And you can tighten up the logic, like using an efficient generator expression to collect the digit characters. It's clean, it's professional, and most importantly, it still passes all of our tests.
All right, Section 5, isolating your tests. We're talking stubs, mocks, and fakes.
To isolate dependencies in larger projects, we use what are called test doubles. It's kind of like using a stunt double in a movie for the dangerous scenes. You'll generally choose between 3 types. Stubs provide simple, predefined, hard-coded responses without any complex logic. Mocks go a step further. They actually simulate behavior and verify that certain interactions happened, like making absolutely sure an email sending function was called. And then fakes are working but highly simplified implementations, like using a lightning-fast in-memory database instead of connecting to a slow, real-world SQL server.
Now, you're going to apply these tools a bit differently depending on your scope. If you're writing class-level unit tests, you're being very fine-grained, testing a single class independently, which means you'll heavily rely on mocks and stubs to completely cut it off from the rest of the app. But if you're doing broader, module-level tests, you're testing how an entire file or package works together. Here, you might actually allow internal classes to interact naturally without mocking them, just to ensure those components really collaborate correctly.
And to execute all of this seamlessly at scale, you're going to leverage an XUnit framework. In Python, this is usually PyTest. In Java, it's JUnit. These frameworks give you the whole shebang: standardized assertion libraries, a powerful execution runner to automatically fire off thousands of tests in seconds, and reporting tools that integrate perfectly into your continuous integration pipelines.
Finally, Section 6, TDD in the real world, the Agile philosophy.
By relying on TDD, developers actively protect themselves against project chaos. When requirements shift mid-sprint, just like they did for our buddy Jimbo earlier, the team can sit down, have a calm discussion, and update the code with total confidence. The test suite acts as an automated safety net, ensuring that new features don't accidentally shatter old functionality. It is literally the ultimate collaboration and stability tool.
Which brings us to a major discussion point in modern development workflows. Given that structured, automated testing like test-driven development is what actually keeps these projects functioning day to day, I want to leave you with a provocative question. Is the traditional, meeting-heavy philosophy of Agile dead, or has Agile simply evolved beyond Post-it notes and daily stand-ups, maturing into these vital, hardline engineering practices like TDD that actually guarantee working software? Think about how TDD impacts your own workflow. Thanks for joining me on this explainer, and hey, happy coding!